Now, quantum mechanics has a reputation for being confusing. I think the main reason for that is that it's often presented as a clash between two inconsistent models. In other words, the wave-particle duality that people talk about when they talk about quantum mechanics, they're really two different models that people are trying to smush together to explain something. For example, for light, we know that light acts like waves when we do interference experiments, and yet early experiments showed and early calculations showed that they also seem to arrive in packets with discrete energies. So really, waves and particles are just limits of the true theory, of the quantum field theory, that was really developed over a large fraction of the 20th century. But the first couple of decades of the 20th century, people were trying to put together a theory for light and matter out of these little pieces, these patchwork pieces of theory, just to try and make something that explained what they saw. And the biggest early success was atoms, both why they exist and how they interact with light. In the early 1900s, it was known that atoms were made up of positively charged things and negatively charged things. It was known that atoms could emit small negatively charged particles. They were then called corpuscles, but we now know them as electrons. And so the dominant model put forward by J.J. Thomson was that the electrons existed in the atom and they were stuck inside a large uniform positive charge. And this was known as the plum pudding model. Thomson described it in more dignified terms, but the fact that these electrons were stuck around like raisins inside a large smudge of positive charge like plums in a plum pudding made a somewhat irresistible analogy. Now, people knew that electrons were inside atoms because they could make them come out, and they also knew that atoms overall were reasonably neutral because they didn't respond to electric fields. And so this idea of having positive charge in there was fairly clear, but it wasn't clear exactly how it was arranged. The first person to really test this model was Rutherford. Rutherford had previously shown that an alpha particle was really just a helium ion. And so what he did was he took some gold foil. The advantage of gold being it's almost infinitely malleable. You can keep on beating it flatter and flatter and thinner until it's almost one atom thick. And he fired alpha particles at it. And an alpha particle was known to be much heavier than an electron, but not that much lighter even than a gold atom. And so he was really firing very heavy particles at this gold and he was trying to see what would happen. So the alpha particles are of course positively charged, and so they should be affected by the positive charge inside the atoms. Now, if the positive charge in the atoms is spread out over a large area, then it turns out that it would only have a very small effect on the alpha particles. And so if Thomson's model was correct, the calculations were that those particles should more or less just go straight through, which indeed they did. But some of them bounced far more than Rutherford expected, and indeed some of them more or less came straight back at the detector. So as they changed the angle of the detector, they could see what angle these alpha particles were being deflected by, and they saw some rare events where they bounced dramatically back. And Rutherford was rather startled by this. He later said that it was almost as incredible as if you'd fired an artillery shell at a piece of tissue paper and had it come back at you. And what this said to Rutherford was that the positive charge inside the atom must be condensed down into a really, really small volume. And so he had a new model of the atom which had a small positively charged nucleus in the center and then electrons going around the edge. And these electrons would be going around in orbit around the nucleus. And that mental model of the atom is still probably the most commonly used symbol for atomic energy and atomic physics today.